Thank you very much for giving me this time to talk. And I'll be talking about a connection between BPS black holes, Instanton condensation, and partially deconfined phase. But in many ways, this talk can be considered to concern the Polyakov loop and how you can use the Polyakov loop in a fairly unconventional way to find a connection between these three things. One of the original motivations for this work is the holographic map, and in particular the best known relationship between n equals 4 CPR mils on S1 cos S3 on the field theory side and supergravity in the ADS side. And a particularly useful thing about this map is that it can map the strong coupling field theory to weak coupling supergravity and vice versa. And we'll make use of this aspect in particular by trying to learn about strongly coupled field theories by looking at the black holes, and in particular trying to learn about the thermodynamics of the strongly coupled gauge theories by computing the thermodynamics of black holes. So this is the application of that. So this is the phase diagram for black holes in AGS5 cross S5. And so we have, at low temperatures and low energies, we have the string gas phase, which is well understood is dual to the confined phase. And at higher energies, we have the large black hole phase, which is known to be dual to the deconfined phase. Connecting these in the gravity is a small black hole. We define the small black hole by the negative specific heat, but its field theory dual is not well understood. So as well as the energy temperature diagram, we can represent this on the free energy temperature diagram as well. And it has the same labels. So this is the large black hole, and this is the gas, and it's connected. The large black hole is connected to the small black hole by this rather dramatic cusp. And so it's a very important question to try and find out what's the dual of this small black hole. And our proposal is that this might be a partially confined phase, which has some properties of the confined and the deconfined phase. So I'll explain what I mean by this. You can consider this to be matrix representing the gluon state of a gauge theory. And the cartoon picture is that some of the colors are in the deconfined phase and the rest are in the confined phase. The partially deconfined phase is relevant in the physics of our real world. So we think that the crossover region of the quark gluon plasma could probably be understood as the partially deconfined phase, connecting the confined to the deconfined regions. It should be relevant physics when the universe was dominated by the quark gluon plasma, which happened a few milliseconds after the Big Bang. And we think it might have a role inside neutron stars as well. But more generally, we think we can learn more about the nature of confinement by exploring the partially deconfined phase and the nature of the holographic map. In particular, how color degrees of freedom could be mapped into the gravity dual. So to explain more about what the partially deconfined phase is, you can start with something more familiar, which are mixed phases where the phases are mixed in space, such as you see with ice and water. So at 0 degrees centigrade, you can get a state where some part of space is occupied by ice and some is occupied by water. The partially confined phase is similar, but instead of being mixed in the space of space-time, is mixed in color space. So so some of color space is in the deconfined phase, and the rest is in the confined phase. And there are some important differences with the analogy to having a mixed space in the space of space-time. In particular, in space-time, you can only have local interactions between the two kinds of phase on the interface. But when you have a mix in color space, you have non-local interactions. Another big difference is the gauge singlet constraint. And so physical states have to be gauge singlets. And so these two properties really define the character of the partially deconfined phase. Yes, and so you see phase diagrams like this also in matrix models, where the only possibility for mixed phase is for it to be mixed in color space, because there's no space-time. A tool that we'll use to understand the partially deconfined phase and to make the cartoon picture of the mixed color space more precise will be the Polyakov loop. So the Polyakov loop is the Wilson loop taken over the temperature direction, and so it represents the holonomy over this compact circle. And you typically measure, you take the trace of the holonomy, and that will give you the expectation value of this Wilson loop or Polyakov loop, and that will represent the energy cost in inserting a quark into the vacuum. But we will be less concerned with the value of the traced holonomy, and we'll focus on the holonomy itself, because it contains a lot more information about the theory. So if we decide to focus on the eigenvalues of this holonomy, then that sets up a standard gauge choice, which means that the eigenvalues are a gauge invariant representation of the state up to permutation of the eigenvalues. So this is telling us something physically meaningful about the phase and the state that we're in. In fact, what it tells you precisely is a measurement of how much of the gauge symmetry is residual in the system. So I'll explain that now. So in the large N limit, instead of treating all these eigenvalues separately, we'll have a density of eigenvalues. In the confined phase, it's known that the eigenvalues will be the center symmetric distribution, and this will be represented in the density by a uniform distribution of the eigenvalues. Likewise, in the deconfined phase, this is characterized by this gap in the distribution. The partially confined phase is a mix between these. So it has a uniform part and a part which clumps and has a gap. So the partially deconfined phase is represented by a distribution which is non-uniform, but it's also non-gapped. And so this uniform part corresponds to the uniformly distributed eigenvalues, or the confined part of the mixed phase. And this is a precise way of referring to this this cartoon picture, because it's well defined to take the eigenvalues of a Polyakov loop and look at the distribution. And so the uniform part measures the residual gauge symmetry in the extended Hilbert space. So by extended Hilbert space, I mean the Hilbert space before you've performed the projection onto gauge invariant states. Yes, so, and you can read off the confined and deconfined sector from this distribution. And so there's clearly a critical point between the gaps distribution and the ungapped distribution. And this was well known from the work of Gross-Witten and Wadier, and it's called the Gross-Witten-Wadier transition, which is when the critical point before the gap forms. And so it marks the configuration between the deconfined and the partially deconfined phases. So if we go back to this picture, in the confined phase, therefore be 0. You mean this P? Yes, so in the confined phase, you can sum over these eigenvalues, and because of the symmetry, the trace of P will vanish. And so it's an order parameter for confinement. You mean symmetric in this sense? Oh, okay. Okay, so going back to this picture that we had of the phase diagram for black holes and for field theory, this would suggest, yes, so this the deconfined phase would correspond to Polyakov loop distribution, which is gapped. The confined phase will be uniform, and then we would expect this partially deconfined saddle to correspond to the ungapped but non-uniform distribution. And in that case, this critical Gross-Witten-Wadier point between these two distributions should occur at this cusp, which is where the specific heat turns from being negative to being positive again. And so this is the same thing on the free energy diagram, where we would expect, therefore, the Gross-Witten-Wadier point to be located at this cusp. So for the weakly coupled field theory, this was calculated in these well-known papers by Aharoni and his collaborators, and it maps well with this. The Gross-Witten-Wadier point appears at this cusp. When we go to strongly coupled field theory, which is what represents the jewel of the black holes, then there are two possible conjectures. One is that the Gross-Witten-Wadier point might occur at this cusp. There's also a new type of black hole which occurs just below the cusp. And there's a Gregory-Laflamme transition which occurs here, and there's a localization which happens on the S5 of ADS 5 cross S5. And there are some arguments for supposing that the partially deconfined phase occurs here. So there are stronger arguments to say that that this saddle after the Gregory-Laflamme transition is partially deconfined, but there are some arguments to suggest that we still get the partially deconfined phase up to this cusp. So then that sets us a challenge, which is to try and prove what is the holographic jewel of the partially deconfined phase, whether it's this, which kind of black hole it is, or if it's something different. And a tool which would seem to be useful for us is the superconformal index, which I'll introduce now.
You know the Polyakov loop expectation is non-zero.
Mm-hmm. Mm-hmm.
That holographic dual must have a horizon.
So you probably expect it to have black hole properties, because especially when you're in the larger limit, then you might, if the Polyakov loop takes, it suggests some kind of clumping of the eigenvalues like you get in the black hole. But I'm not sure if there's a strict argument.
It's calculated polygraph.
You can calculate the Polyakov loop expectation value, but it's the eigenvalue distribution which is difficult. So you can consider multiply round d-branes, but in order to determine whether the distribution is gapped, you need like an order n of those d-branes, and so you need to back react the geometry, and you get difficulties.
So nobody's ever done that polygraphically?
I don't think so. I don't think so. In some ways, that's what I'm trying to do, something like that, but using the index, but not using wound d-branes. Yes, I'm trying to use the superconformal index. This can be understood analogously to the Witten index, but by using the state operator map, you can use very similar arguments in superconformal field theories. So this is the expression of the index. By the Witten arguments, it's invariant under this value of beta. So it's invariant under our normalization group flow. And that means that you can form calculations at weak coupling, and they'll still apply in the strong coupling phase or in the strong coupling region. So that's what makes the superconformal index so useful. But in order to have this property of invariance under RG flow, you need to have this grading. So the index counts opposite signs for bosons and fermions. It's possible for the BPS states to cancel in the index, and then it wouldn't be a very good approximation to the count of BPS states, but it will serve as a lower bound to the number of BPS states. And in that sense, we're using this as an approximation to the regular partition function. So we'll be treating this index as if it's the partition function of the theory. And we're also free to insert a few chemical potentials in here. So here we have three chemical potentials from the R charges. So in the field theory, these come from the SU4 R charge. In the gravity theory, they correspond to rotations of the S5, which has SO6 symmetry. So they have corresponding charges. And there's also the angular momentum in both theories. So rotations either in the field theory or in the AJS5. And you can insert these to calculate the index at different values of the chemical potential. So this will be our strategy, to use weak coupling techniques to approximate the strongly coupled partition function, and then we can compare the strongly coupled field theory results to the holographic dual, and then try and align them with the BPS black hole phase diagram. But first, I'll make a simplification. So instead of having 5 independent chemical potentials, there's actually 4 because of constraint, but we'll set this relation so that there's only one chemical potential that we vary. So this is like a symmetric weighting of the R symmetry and the angular momentum. So it's about the simplest setup that we can imagine and have non-trivial chemical potential. In that case, we have something analogous to temperature. So we define the supersymmetric temperature to be the inverse of the chemical potential. And we find that if we do that, then the phase diagram for BPS black holes looks very similar to the phase diagram for thermal black holes. Yes, so there's a constraint which means that when you sum the chemical potentials, they have to vanish, and these will have opposite sign. So in order to satisfy that constraint, which I haven't shown here, then you need to take this particular x squared and x cubed value. So yeah, so it's like the ratio between the product of the R charges and the angular momentum has to be 1. So you have x to the 6 on the top and x to the 6 at the bottom equals 1. So that's why. And of course, because we need to preserve supersymmetry, then we can't introduce a real temperature. So even though we use this term supersymmetric temperature, we're actually at chemical potential instead, and that will prove to be crucial for understanding our results later. So to calculate this, we'll use a path integral method. It was shown by the work of Aharoni and his collaborators that if you take a weakly coupled Yang-Mills theory on S3 equals S1, then you can integrate out lots of the higher modes, but the mode over the S1 has a 0 mode, so you can't integrate that out. Yes, so we can represent this as the index as a path integral over the modes over the S1, and these modes over the S1 are the same as the Polyakov loop, so you can represent it in terms of the eigenvalues. So crucial parts here are instead of integrating over the gauge group, we turn it into an integral over the eigenvalues, and that gives us a Van der Monde determinant here. And it leads eventually to an expression for the index, which we can write in this form with something in the exponent, which represents this. So this comes from the Van der Monde determinant, and it looks it looks very amenable to doing saddle point analysis. Yes, so our approach will be to find the saddle point of this action, and then the prescription for finding black hole saddles is to find the charge and and set the charge to be real, and then we can calculate the free energy via Legendre transformation. And so this gives us a matrix model in terms of the Polyakov loop eigenvalues. This action looks a lot like a 2D Coulomb gas, so that's one way you can imagine solving this matrix model by finding stationary points of this 2D Coulomb gas distribution. And in order to make this calculable in practice, then we truncate the modes in the distribution to a certain number p, and so we'll find that as you can increase and include more and more modes in the distribution, and then your answer will get more and more accurate. So that's the approach that we'll take. Yes, so a crucial point to this is that we need to find complex saddles of this action. If you take real saddles, then there's this catastrophic cancellation between bosons and fermions in the index, and so for a long time they couldn't see the order n squared black hole entropy because of this cancellation. but this was resolved by looking for complex saddles instead. But that means that the fugacity x that I introduced before has to take complex values as well, and the eigenvalue density distribution has to be moved into the complex plane, so it no longer just sits on the unit circle. So instead of a distribution on the unit circle, you get more complicated distributions like this. So this barrier boundary between red and green regions is where the eigenvalue density is has support, and in this case, it looks looks very different from the unit circle. And so these represent the saddles of the in terms of the eigenvalue distribution. Yeah.
I think of the eigenvalue dispositions.
Well, that's interesting. So yeah, so that's something that I would speculate on later, but it would be interesting if we can make that identification. So these grey points represent the boundary of the eigenvalue distribution, the eigenvalue cut. These other points represent stationary points. So in the 2D Coulomb gas picture, it means you can take an eigenvalue and move it to one of those points, and that will represent another stable distribution. So that will be important later, but I haven't explained why yet now. And the grey is the endpoint of the distribution. So it's where the eigenvalue density goes to 0.
So confined, I would just see circles.
Yes. Yeah.
Confined, I would see.
You'd see something like this. So in the complex saddle case, these grey points don't overlap, so that means there's a gap. And in the if we were at real fugacity, then this would just sit on the arc of a unit circle. So then performed this calculation to see what kind of thermodynamic phase diagram the index would give us, and it gave this. So the gapped phase corresponds not just to the large black hole, but also describes the black hole past the cusp and all the way down to the very small black hole limit at infinite temperature. And so this is all described by the gaps distribution, and the gas is the confined uniform phase. So the only place where the ungapped distribution could be was around the black hole string transition at where the free energy or the entropy to order n squared would be 0. So that led to that suggested a kind of paradox, because from the partially deconfined field theory analysis, the entropy should be of order n squared, but from this calculation of the index, it's found that the entropy is much smaller, as if it doesn't correspond to a black hole state at all. So this was confusing for a long time, but there are two points to resolve this paradox. So the first is to remember that we're actually using chemical potential, not temperature, and this can lead to an explicit breaking of gauge orbits, and it can cause it demands a new interpretation of the Polyakov loop eigenvalue distribution, which I'll explain next. The second is that we should check for instanton condensation in the phase diagram. So
Phase diagram you showed, that was just
yes, yeah.
you never showed the phase diagram from the plot.
Yes. Well, it looks very similar to this. So yes, so the this one that I showed before. Yes. So this is the holography phase diagram looks just like this. So when you said holography, yeah, the BPS black hole phase diagram, it looks just like this.
Looks like that with a small black hole.
It doesn't have this as far as people know. Yes, it has the cusp and the small black hole and the large black hole. Yeah.
Problem is that these formal index calculation is missing that order in
Yes, or it suggests that the Grosser-Witten-Woddy point is actually yeah, down here instead of somewhere along the small black hole saddle.
Because it's protected, doesn't it have to be exactly?
Yes. So yeah, so the holographic the gravity calculation just shows that these branches exist. It doesn't say whether it doesn't say what it should correspond to in the polygon loop. And our argument that the Grosser-Witten point should be around here was based on field theory analysis. And so our prediction for the thermal black hole was that the Grosser-Witten-Woddy point could be at the cusp or somewhere along the small black hole. And then because the BPS black hole phase diagram looks just like the thermal black hole phase diagram, then we reasoned by analogy that it should be the same. At this stage, I haven't proposed any new transition yet. So this was already known from BPS black hole phase diagram. You can't see the relationship to the Polyakov loop from the gravity side. No, there's no new prediction from this point. Later, I'll suggest something like a new phase, but okay. Yes. So so one resolution which it seems which this one resolution came from an understanding of the quark gluon plasma in the real world. So in that case, there are arguments to show that the Grosser-Witten-Woddy point occurs before the transition to the partially deconfined phase in some situations when you have a high chemical potential. And the reason for that is that the chemical potential causes baryons to condense, and the baryons explicitly break the gauge stabilizers of the state. So in that, so that if you take a Polyakov loop and try and measure the eigenvalues, then it would suggest that there's no residual gauge symmetry because of these baryons, even though the gluons could still be in the partially deconfined phase. So if that's the case, then yes. So yes. So I'll explain that the connection in a little bit. So that led us recently to propose this new phase diagram for the quark gluon plasma, which I won't have time to get into, but it was in, so this is the connection to n=4 super Yang-Mills. So instead of baryons, we could have other objects which break the which explicitly break the gauge symmetry when they condense. So one option could be fuzzy spheres or determinant operators. Yes. So if this explanation is correct, then it would suggest that this small black hole saddle could still be the partially deconfined phase, but it could have some condensation of these other objects, whether they could be giant gravitons and fuzzy spheres instead. And that would be one way, that would be one consistent resolution. But it's still quite unsatisfying because the question remains, how can we identify the partially deconfined phase in that case? And I think the answer might be to think more carefully about other contributions to the partition function, which are known as instantons. So a partition function in general will be described by a trans series like this. So this is a part which could be reached by perturbation, but they're very generically non-perturbative contributions as well. And in fact, it had been realized as far back as 1981 that these instantons are important in matrix models of eigenvalue distributions, like the ones they've been discussing in this talk, and in particular in the so these are called instanton contributions because of this exponential suppression and because they're non-perturbative. But they manifest in in matrix models like with eigenvalues like this in the following way. It turns out the eigenvalues themselves can tunnel to another stable point. So this point on the circle is always stable. So if you imagine the 2D Coulomb gas picture, you can imagine that it's getting symmetrical propulsion from all these eigenvalues. And so this point will always be a stable state. And to the partition function, it contributes an exponentially suppressed amount. Likewise, it was shown that you can keep taking more eigenvalues and creating new instanton contributions. And it turns out they must line up on the real axis. So they're extended to the complex plane. But if you treat these eigenvalues the same as other eigenvalues, but just extended to the complex plane, then you can do the same calculations with the action, you can use all the same tools. And so that's how instantons are described in this matrix model. But it's been known in other contexts that the instantons which come from eigenvalue tunneling can correspond to actual topological objects in field theories or wrapped D3 branes in holography. And they're the remnants of the dimensional reduction to the matrix model. So so this was first identified by relating matrix models to their 2D string theory, non-critical string theory duals. But particularly interesting for me is this quite recent identification where they found that tunneling eigenvalues in the uniform distribution correspond to D3 branes, which are wrapped like giant gravitons, and describe configurations around the thermal gas configuration in n = 4 CPN mils. Yes, I think so. Yes.
The signature
Mm-hmm.
you're saying there are also tunneling units. The signature when you have
Yeah. Yes. So they could relate the actions from these D3 branes to the tunneling eigenvalue, and they correspond to the D branes. Yeah. Okay. I think they calculated the action, but yeah. Yes, and so it was understood that that the instantons actually play an important role in the standard Gross-Witten-Wodier model and similar models, because as you approach the Gross-Witten-Wodier point, the critical point, then the action, the instanton action vanishes, so you can no longer neglect them as being exponentially suppressed, and they must play a role in the actual transition. So this would correspond to the transition between the deconfined phase and the partially deconfined phase, and suggests that you have to be aware of instantons in this transition. So that made me suggest that instantons in general could condense at the transition between partially and the completely deconfined phases, and it might offer a new signature for the partially deconfined phase and the transition. So I suggested this to Hanada and Watanabe, and they tested this on a model which is very close to real-world QCD. And they tested it by examining the topological charge distribution as you change temperature. And they found indeed that agreement in which where they expect the partially deconfined phase to begin and the crossover of the quark-gluon plasma to begin. They also find that these topological optics are condensing. Yes, so this is it's like QCD, but they have heavier some heavier up quark or some heavier quarks, which make it slightly easier to do the lattice computations. Yeah, so it's very similar to real-world QCD. Yeah, and so this could have other connections. Like there are other reasons to suppose that chiral symmetry breaking occurs at the same point by using a drift anomaly argument. But instanton condensation can also be implicated in chiral symmetry breaking. Also, it suggests that the crossover in QCD might be an actually third order phase transition, since you're going from this dramatic phase from no instanton condensation to having finite instanton condensation. And it might, if we do further work, then it might also connect to some mechanism of confinement. For example, they might be related to the instantons which appear in the fractional instanton liquid model. But this was an aside to talk about real world QCD. And then we'll take what we've learned and apply it to BPS black holes. So something which was, it turns out to be crucial that we take complex chemical potentials, because this means that there are some regions in the coupling space where multi-cut saddles actually dominate. So this was realized already in this paper on delayed deconfinement, but these authors didn't look at genuine black hole saddles. Yes, so this coupling is a coupling in the Gross-Witten-Wodier model, and so you can think of it as a way of parameterizing the chemical potential on saddle. And so in the original Gross-Witten-Wodier model, you lie on this real line, and you can see that instanton condensation takes place at the gross Witten-Wadier point. But if you can take, when you take values of the coupling in the complex plane, then there's this critical line where you go from the phase where the gapped phase dominates to where multi-cut eigenvalue distributions with tunneling eigenvalues can dominate. You might think that you have to consider Lefschetz thimble analysis to check whether these multi-cut saddles are actually dominating. But there's you can evaluate this. There's an exact expression that you can evaluate numerically, and you can see that there is a genuine phase transition here as these new multi-cut distributions begin to dominate. So I applied this to the black hole and checked for instanton condensation, and I found that it seemed like there really was an instability along the small black hole saddle.
Matrix model.
Yes. So this is the first truncation, the first approximation. Not quite, so almost everywhere, but if you zoom in, then you can find that to numerical precision, it doesn't actually reach the cusp, but it's very, very close to the cusp. So yeah, so that would seem to suggest that there's a new phase which dominates in the microcanonical ensemble along this small black hole saddle. We go to, yes, so in this diagram, the coupling follows this green line, and you can see that it enters the multi-cut region. So this takes place just near the cusp at the instability. So multi-cut distributions begin to dominate here. Yes, from the index calculation. Sorry. Oh, so this picture is just from the matrix model, taking and then they did this calculation using the index similar to my own, but yes, because they didn't look at the actual black hole saddles where you have to do the Joindler transformation and set the charge to be real. They were looking at deconfinement curves. So in that case, you don't see instanton condensation, but when you look at genuine black hole saddles, then you do see instanton condensation. Okay. So then to check this isn't just a property of the approximation, then I went to the next truncation. It's a bit more complicated because there are two viable saddles now, but this blue one dominates the entropy, so this is the important one, and you again see that there's an instability very close to the cusp. It's moved a bit down from the cusp, but it's still very close and seems to cover most of the small black hole region. And then I went to p equals 3 and did the same thing again, and again you see that the instability seems to persist to this level of the truncation. There might be something interesting going on in the subleading saddles as well, but there seems to be a transition involving a different kind of instanton, different kind of tunneling pattern of the eigenvalues. Because if you look at the charge, we're in the microcanonical ensemble, so you measure the entropy at a specific charge, and it's always this blue one which has higher entropy. Because in the ground canonical, then the small black hole is never dominant because it has negative heat capacity. Yes, so that's something I haven't explored much, but it could be interesting. So these are the three truncations shown next to each other for comparison. So I think this shows that the instability is persisting even though it's moving away from the cusp a bit. And then this is the instanton action itself against the supersymmetric temperature. So you can see that when the action goes below 0, then instanton begin to condense and multi-cut saddles dominate. Yeah, that's zoomed in. This is these values represent the accuracy of the truncation. So you expect corrections to the calculation the corrections would get smaller and smaller. So so I think that's an argument to suggest that it's not just an approximation of the it's not just an artifact of the approximation, but this instability really does persist. Interestingly, there's a different approach you can take to the index and calculating BPS black hole saddles. And this is the beta ansatz. And these authors found something which they thought could be an instability, which also lies along the small black hole saddle. But it takes a very different guise. It looks like a set of competing saddles, which compete by Stokes phenomena between the saddles. And it lies in a similar location to the instability that I found. So it seems very likely that they're related. So one possibility is that maybe if the eigenvalues seem to be related to D3 branes. For example, if you remember in the paper I mentioned before, where the eigenvalue tunneling corresponds to D3 branes wrapped as giant gravitons. So maybe the same thing is happening again here, where the instability corresponds to D3 branes wrapping in a certain way. But this was explicitly checked as a result of this beta ansatz result for giant gravitons, or branes wrapped like giant gravitons along the S3 over the S5, and they found that there was no instability against these kinds of D branes. It's possible though, and the authors acknowledged this, that you could have a different kind of D3 brane wrapping, like possibly a dual giant graviton. And there are some results which have black holes with this kind of instability with dual giant gravitons. There's this one in which these D3 branes separate from the black hole and wrap in an S3 around the ADS5 due to a chemical potential. So that's quite similar to what we've looked at in the BPS case. There's also this result on dual dressed black holes, which are these black holes with dual giant gravitons around them. But they didn't see this using their mechanism for the charges that we've looked at in this talk. But there could still be a relationship somehow. Another possibility is that maybe we have a Gregory-Laflamme style transition in the BPS black hole case as well. So there have been arguments against a Gregory-Laflamme transition in the BPS sector, but they rely on an assumed endpoint where the black hole, the endpoint would be where the black hole is so small that it's as if it's in 10-dimensional flat space. But it's possible that there are other endpoints. In the thermal black hole case, it's been found that configurations with belts of black holes, black belts, would also be thermodynamically favorable compared to the standard small black hole. So something similar might happen here, and it's possible that this could even represent some kind of hairy black hole, if it's localized, which people have been looking for hairy black holes in N=4 super young males, and it's dual for a while, so there's that possibility. And a third one, which would be consistent with the partially deconfined phase interpretation, is that it could just be some other kind of multi-center BPS black hole solution. Yes, so and on the field theory side, there are some basic properties which are immediately apparent, which is that this gauge symmetry breaking in the extended Hilbert space, because these eigenvalues are tunneling. We expect what the instantons, whatever these instantons here are, would be continuously connected to the gross Woodin-Wardier instantons, which are the instantons we found in QCD, which seem to appear between the partially and completely deconfined phases. So that would suggest some kind of physical connection to the transition to partial deconfinement and to some kind of confining mechanism. You can measure the degrees of freedom using the trace of the holonomy, the Podekov loop, and that also experiences some kind of phase transition because of these tunneling eigenvalues. So that's another thing to suggest that this could be the partially deconfined phase. I didn't have time to go into it, but the driving mechanism behind these eigenvalues tunneling is the same as the mechanism which drives the gross Woodin-Wardier transition and the emergence of a non-uniform part in the field theory. So two natural proposals would be that this represents the partially deconfined phase, or it could be something like Higgs phase. Like the paper by Henriksen and his collaborators on the previous slide suggested. But these might be related by the standard Fredkin-Schenker argument as well. So perhaps these should be treated as the same thing, where a partially Higgs phase is just is a similar description as the partially deconfined phase, but at a different coupling strength. So there's a lot of future work which is possible, but some immediate suggestions are that we could try and identify what these instanton objects actually are on the field theory and the gravity side. Like, it would be very interesting if they are D3 branes, because that would tell us a lot about the how color degrees of freedom are mapped under the holographic map. And if we can identify them in field theory, then that might tell us whether about topological objects which might be crucial to the mechanism of confinement. And as I explained, I used a simplified region of the superconformal index where we only had one variable describing the chemical potential. But if we introduced more independent chemical potentials, then you can derive, you can find certain condensates and other properties which might tell us a lot more about what these phases are. I think since this people hadn't realized this instanton instability before in this model, so it's possible that there are other setups where this kind of instanton instability is present, and it would be interesting to look in other models as well to see if it's there. And also I'm very interested in comparing what I found here to the beta ansatz approach and seeing how it lines up with their explanation and why it seems like instanton condensation in this approach compares to Stokes-Saddle competition in the beta ansatz approach. So in summary, even if this doesn't have any connection to the partially deconfined phase or other things I've spoken about, I think there's evidence for a new kind of phase in the n=4 super-Yang-Mills model and the BPS sector. And so I want to find out what this instability is and find out more properties about it. So that's what I would finish with thinking about.
People looked at the supergravity solutions for the small black holes. Which instabilities did they look for?
So they yes, they looked at D3s which are wrapped on the S3 and the S1 of the ADS5. So yeah, that's right.
Didn't see any.
Yeah.
Did Erickson, Hoyos, and Bogler see an instability?
Yes, they saw the D3 brains being ejected from the black hole and being wrapped in the S3 of ADS5. Which ones? These ones? Because they didn't check for that kind of solution. Well, also this one doesn't apply to BPS black holes. These are more general black holes in this paper.
I thought people had seen it.
Seen what?
Maybe not globally, yes.
Mm-hmm. They see it in the BPS sector.
Not BPS, but like charged black holes,
Mm-hmm.
brain, you'll see that it gets pushed away from the horizon.
Mm-hmm.
I think the physics is probably similar, that because of the chemical convention, it returns some kind of wave direction.
Mm-hmm.
There it was simpler because in point grace, have a flat directions to start with.
Mm-hmm.
Okay, well, so but I don't understand why those are the
Yes. Okay. So this paper did identify. So in the
That's the tunneling. So you're supposed to imagine you're tunneling through the black hole.
it just tells you about the thermodynamics. So it just tells you that the configuration with a D brain away from the black hole is favored relative to the case where all the D brains are in the black hole. Well, the Instanton would describe the tunneling of the D brain to somewhere outside the black hole.
Yeah.
Well, it is. I'm proposing that it might be. I need to do more work to check.
And also, there should be there's definitely an instability.
What do you mean?
Have they found an instability solution?
In the beta ansatz approach to you. Yes, but their work didn't apply to the BPS sector. It applied to other kinds of black hole.
So nobody's seen an instability of the BPS.
Yeah, I don't think so. So this paper suggested that there might be, but they didn't have conclusive evidence for that.
It's not gravity calculation.
This was an index calculation. So these people checked whether the D brain wraps on the S3 in the S5. But I'm suggesting that maybe the D3 brain wraps on the S3 in the ADS5 instead. I don't have good evidence for that yet. Yes, we've only just considered what happens when we have finite chemical potential. So most work has been done at 0 chemical potential and just changing temperature. So we expect a crossover to occur. So yes, so our expectation is as you increase the temperature, you go from the confined phase to the partially deconfined phase to the completely deconfined phase, and that corresponds to the well-known crossover region of the quark-gluon plasma. So the crossover in our proposal is the partially deconfined phase. And then as you add chemical potential, you have to contend with the possibility of baryons condensing as well. So, so that makes the story a bit more complicated. But the partially deconfined phase can exist in that case as well, we think. Well, there are a few suggestions. So one could be, we might have to identify what the instanton actually is first. So if it's, say, the object which appears in the fractional instanton liquid model, then finding evidence for monopole instantons condensing at that point would be good evidence, be interesting. There's also a prediction about linking that to a third order transition instead of being a crossover. But yeah, that wouldn't be so strong a prediction. Yes, so I've glossed over this, but in the quark-gluon plasma, because the matter content is different, then the unstable saddle representing the partially confined phase can become stable. And yes, so we think that that is actually a stable configuration in the grand canonical ensemble. So it should be physically relevant in those cases.